Let's use our knowledge about modified virtual work to create a finite element. This will be a variational approach, an energy approach, and will replace the equilibrium ideas we used earlier. The equilibrium ideas were okay for statically determinate structures because the person could use equilibrium laws to balance the little element and actually could figure out what was going on inside. But a typical finite element with a number of nodes has load paths inside that are not clear to the engineer. So therefore we like to use energy methods in statically indeterminate systems. The philosophy is a lot different between this approach and the older equilibrium ideas. I'd like to give a homely analogy about that difference. If I were to use equilibrium concepts and tell an automobile driver how to proceed from Detroit to Chicago, I would tell very much the path involved, that you start in Detroit, you go west 180 miles on I-94, and then give a very detailed path-dependent idea of how you go from point A to point B. The variational method is different, though. You would tell the driver, well, just drive around in the United States, and then stop somewhere and get out of your car and walk a little south and smell the air. Do you smell stockyards? And see, that might be Chicago, okay. Then you walk west a ways from your car. Do you get out on a prairie and see the beautiful plains of the Midwest? Then you go north a little bit, and do you hear a football game? Perhaps Northwestern is playing a football game in Evanston. And if you go east some distance from your car, do you splash into a lake? Now, by that testing in the neighborhood of the solution, you are doing a variation, and then if those conditions are satisfied, you say, you are in Chicago. And it's a little bit magic, a little bit like lifting yourself by your bootstraps, because you presume that you know the answer and you're testing the answer. And so you concentrate a little bit more on the dependent variables in the problem and a little less on the independent variables in one sense. Well, in any event, we're going to follow that logic through the variational approach to creating finite elements, and we'll have a little problem session at the end. We'll start out our derivation by repeating some of these motivational ideas. Most finite elements really are statically indeterminate, and the energy methods really work well for these redundant structures. Also, the method generalizes rather well to nonlinear elastic problems, so there are some problems that are rather easy to handle. And an interesting side effect is that the virtual work theorem emphasizes a displacement field and does a good job on predicting it, but doesn't do so well on the stress field. That's a paradox because this is probably the best and easiest method, and yet the results are not often what one would want, for instance, in mechanical engineering, which is more stress-oriented. In aerospace engineering, sometimes displacements really are important in terms of stiffnesses of structures under air loads, where you might get aeroelastic flexibilities that are very crucial. Let's derive the stiffness matrix for a simple element that only has concentrated forces on it. Later we'll come back and look at distributed forces such as gravity. Here is a four-noded quadrilateral. I show a load at one corner, and I show the three positions. I show the undeformed black body, the deformed red body at state 2, and then the green virtually displaced body. We're going to use the assumption that the material is energy conserving, and we're going to pass from an incremental approach that we used earlier into a variational approach in which we consider delta to be a variational operator that can be separated from the function on which it acts. So there will be a unique displacement field in our problem. I like to write down the vectors and the matrices that appear in the finite element formulation in a flowchart form. On the right we have the elemental nodal coordinates signified by a Roman U and a subscript E. On the left we have the nodal forces. So those are the finite element quantities. Then we have the classical stress, strain, and field displacement in the middle. There's a vector of generalized coordinates that link those two. Some of the mappings that we've discussed already are the displacement function matrix phi that goes from the generalized coordinates to the U displacements, and those are polynomials. And then we have the H matrix, which is needed in the inverted form that relates generalized coordinates and nodal coordinates. But more often nowadays we use the shape function as a mapping, as a primary mapping, and jump directly from the nodal displacements to the internal displacement field, signified by this italic U. And there's also a strain matrix B that will go all the way from nodal displacements to internal strain field. The D matrix is a displacement relation. It's a strain displacement and has derivatives in it. The G matrix is a material property. It's the generalized Hooke's law and would have a dependence on the specific material and could be orthotropic or have exotic anisotropies in it. So we've got the mapping from one vector to another, but we are short one mapping, and that's the equilibrium one, which we would have preferred and which we used to use. It's as if a person were standing on one side of a desert island that had a lot of chasms on it, and there was a banana tree on the other side, and he really was hungry. So he might start trying to cross these chasms, and he would find there are convenient bridges over each of the chasms until you get to the final chasm here, which unfortunately is the equilibrium chasm. And we really are not able to build a bridge there. So it's quite a paradox for this hungry person to figure out how to get something to eat when he can't jump the last chasm. I'll write down the modified virtual work theorem for you here. And on the left is the work done by the external forces during a virtual displacement from state 2 to 3. The next term is a change in strain energy during that same virtual displacement. This term on the left is relatively easy to handle. Below, we find that it's the change in nodal displacement times the nodal forces themselves. And that's the fundamental definition of work. It's an inner product, and so it sums over all of the nodal degrees of freedom and nodal forces. So that's relatively straightforward. But the change in strain energy is most fundamentally defined as a change in the strain energy density, which is a per unit volume energy. So you have to have the change in strain with an inner product with the stresses at the equilibrium state. That has to be integrated over the volume, and then that would be the total change in strain energy. We need to discretize this right side here in that we've got to convert from field variables inside the element to nodal quantities. And we already know how to do that on strain itself. It's the geometric relation B times the nodal displacements. Then if we'd like to find the virtual strain, and by that we mean the change in strain that occurs with the change in the nodal displacements, it's possible by using the delta as an operator on the two sides, and then realizing that this delta operator acts on dependent variables, not independent variables. You're changing the answer, not the underlying problem statement, and so it doesn't affect the B matrix at all, but rather attacks only the displacements at the nodes. So that operator passes through the B matrix and acts on U as shown here. Then we take the stress definition as the product of the material law and the geometric law, and acting on the nodal displacements. Now those two quantities are crucial here in the strain energy, and I'll write those in our next figure. We'll insert those two important quantities here with the change in strain on the left and the stress on the right. Now, because the change in strain occurs in transposed form, a transpose of a product is the product of the transposes in reversed order, and that's why the delta U is on the left side of the B matrix. But furthermore, the nodal displacements U and delta U are not functions of the underlying coordinates x, y, z, and so they're not affected by the volume integration. They appear to be constants in this calculation, and so you can bring them outside. So we do that. We bring both those two terms outside as shown in the next figure. Then we use the additive and multiplicative property of matrices and the fact that that's distributive to sum the terms in this way and then carrying the remainder terms in this large set of parentheses. Now is when we will convert from a scalar concept to a vector concept. And the logic is this, that here we have a row vector times a column vector. And when the inner product is taken, which is a scalar product, there's only one term there, like 6 inch-pounds of energy or 12 Newton meters or whatever, to be 0. But the trick is that this is an arbitrary displacement. And so as the driver of the car when he was in Chicago had to do, he had to get out and walk around the car, north, south, east, and west. Likewise, in a structure, you must vary the different coordinates in the element, and to ensure then that this vector in parentheses is orthogonal to all possible changes in the node positions, the only way that can happen is if the quantity in parentheses is itself 0. And so you bring the argument from a scalar one to a vector one because of the arbitrariness of that one pre-multiplying vector. And that then recovers what is really an equilibrium law here and is a vector law. And we identify immediately that what we'd like to call a stiffness is this integral. And that indeed is the finite element stiffness matrix, and summarized in the equation of equilibrium below. This is very compact and works for a wide variety of elements. I think it's really interesting that the finite element derivation, which is so powerful on the previous two slides, only took 10 lines of equations. And of course we had the background of the modified virtual work theorem in preparation for us. But it's a very powerful technology and so general, so it's very important to understand that. Now, as we look at this island again, what we find is that in that expression, which I've repeated here, you involve one of the bridges twice. You take the geometric law and it's symmetrically disposed about the material law. Kind of as if the man had jumped over this nice strain bridge, over the material bridge, jumped back over on the this geometric law, and found himself standing here at the beginning with a banana in his hand. And so he got the full value of having made it all the way to the banana tree. And indeed, we're able to fix up then the system behavior of this system without ever directly closing the one gap. And we've used energy to do so. So that's the magic of the variational process. Now, when you do actual calculations, it's important to have different versions of that calculation available involving these different bridges. And the most common form would be the second one here, where we use the shape function and then the strain displacement law in separated form, at least at the outset, because many people would start the whole derivation with the assumption of the shape function. Another form which I thought had died out, but which is still interesting to some people, is this bottom form where the H matrix is separated out and indeed can be factored out of the inside of the matrix because it's a matrix of constants, leaving the variables shown. This has come up to be useful in a recent derivation of what's called geometric shape sensitivities, and I was just amazed when I saw that. This was originally the old-fashioned way of doing the problem with the displacement functions assumed first, then the mapping H found, all the inversion, and so on. And there was a form called Argyros's natural coordinates that makes use of this form. Well, that finishes the derivation of stiffness for a typical element. Now we need to go back and look at how to handle distributed loads. In this case, you can have volumetric, surface, and line loads, and I show those on this fat little potato over here. The surface loads would be given the symbol T for traction, L for line loads likewise, and this X for volumetric loads. And gravity would be the biggest example of a volumetric load. Pressure would be the biggest example of a surface load. And line loads come up more typically on beams, so I've included that as a subcase. How can we redistribute these distributed loads and make them appear as concentrated loads at isolated grid points? That has been a general interesting problem in finite elements, not so much just for static loads, which we'll do here, but also for inertial and damping loads. So there are other cases lurking in the weeds, you might say. Now, we're going to again use the modified virtual work theorem, which works out beautifully on this. And we'll repeat the previous derivation and then add the external force terms. I will hurry through the strain energy part of the problem since we've spent time on that earlier. I'm going to write down the modified virtual work theorem again, but include the work done by external distributed forces. And they appear here, here, and here for the line, surface tractions, and volumetric forces, respectively. In each case, you'll notice that the distributed force acts through a change in displacement in the interior of the body. And the dimensions are such that when you do this calculation, it's an amount of work done per running length of line. So you integrate up on the line length. Here you get a surface effect where there's an amount of work done per unit area, and you integrate on per unit area. And lastly, the third volumetric force is integrated over the volume. We have already worked out the contribution here in the change of strain energy over the volume. So our biggest task now is to discretize and convert that from integrals over the interior of the element into quantities happening at the nodes. The shape function is our biggest tool for that. So the internal displacement field can be interpolated in terms of variations in the nodes themselves. And as we saw before in our original derivation, the transpose of a product is the product of transposes in reversed order. So when we want this term to appear, it will bring the delta U out front in every case in that integral form, and then we can factor that out from the integral. We'll use the fact that the multiplication and addition are distributive, and we'll gather the terms as shown. We now have a shape function appearing in these distributed work terms, and also appears in the stiffness, by the way, hidden in the B matrix. So this entire exercise really depends on the interpolation of the internal displacement field. We now use that same argument again about the fact that these are arbitrary virtual displacements, and the only way that the term in large parentheses can cause a zero energy under an inner product with an arbitrary vector is that the quantity in parentheses itself must be zero in a vectorial sense. We can identify in that equation the contribution made by the stiffness matrix as we did before, and then we can identify the contributions of each of the external distributed forces. We have the line, surface, and volume forces. So the quantity in large parentheses is brought out and made to stand alone as an equilibrium vector law that I'll write here. I'll separate out the stiffness term on the left and put all of the force-like terms on the right. And the original concentrated forces F appear standing alone, and then we get these inner products for the others. We will give a new symbol for these called equivalent nodal loads for the original loading of interest, the line, the traction, the volumetric loads. And from that point on, we can bring these equivalent nodal loads into play. These quantities that I'm putting in square boxes here are the ones that are automatically done by computer codes for the user. So luckily, if your loading is of a rather standard form, such as constant pressure and often linearly varying pressure, then you will have the help from the computer code to put that in for you. In the bottom, I have shown a typical continuous body with finite element nodes on it, which then might form an element itself. There's some patch that has, in this case, a surface load. And of course, what we're doing is a replacement idea. We are replacing the pressure on that surface with these concentrated forces over here, which are then called equivalent nodal loads. Some people would call those equivalent work loads or work equivalent loads. Well, you might think that we've finished our work now, that we understand distributed loads. But there really is another category of initial effects that are due to initial strain and initial stress. And these are so useful in thermal problems and in nonlinear problems that I'd like to solve that issue now also. This will be called a derivation for initial stress and strain. And of the two, the pre-strain is actually more important because of its use in the thermal problem. It's possible, it turns out, to treat a temperature field on a body as if the body had instead had a mechanical strain. And that's what we will prove in detail here. Also, in nonlinear cases, it's used as an artifice to account for either material or geometric nonlinearities. And pre-stress is used in that artificial way also. Now, what we're going to do is redo the derivation, and we're going to generalize the stress-strain law this time to include an initial strain and an initial stress. And I know this isn't too motivated, although at the early start of the virtual work discussion, I did show that the stress-strain law might be biased in this way in general. So actually you have seen one reference to this without any motivation at the time. Now we know that these are actually very useful in practical cases, and especially in thermal problems, in thermal stress problems. Okay, well, we still have the general idea that the change in strain energy is the change in strain times the full stress at equilibrium. And now we just expand that, having a more general view of what stress is, and we put it in this parenthetical quantity here. Again, the transpose will allow the delta U to be brought out front. In this derivation, the pre-stress and pre-strain are going to affect the variation of strain energy, not the external loads. So I'll work hardest on that strain energy term. Here we have the change in strain energy that would include the previous term, which had to do with the variation in displacements, but now it also has a term regard to variation of this initial strain entering in. It really goes along for the ride in the energy calculation, and then the stress also goes along for the ride. So these work-like terms are interesting because you get a change in the, here is a change in the nodal displacement, and then you get these various terms that ride along at state 2, at the equilibrium or balanced position of the body. And this is the conventional linear elastic term, and then our pre-strain and pre-stress terms. Now, if we just combine this information with our previous energy statement, which was a modified virtual work statement, then we get this longer form. And I'm now identifying the quantities in here as being quantities with a new purpose here. The equivalent nodal load due to pre-strain and pre-stress. There's a sign convention that goes along with these. By the time you put these terms on the other side of the equation from the stiffness term, then the signs are changed so that we do get this minus sign cancels on this term, but we will get a minus sign on the stress term shown here. We've certainly done a lot of good work to this point. We've developed the element stiffness, and we've done a lot of work on equivalent nodal loads. I'd like to make some comments here, primarily about the equivalent nodal loads. First of all, we have developed 5 equivalent nodal load types. That's a lot. We have a lot of power there. And these equivalent nodal loads have been implemented in most commercial codes for many kinds of volumetric surface, line, and thermal loads, such that if the user inputs a certain temperature field at the grid points, then the code will automatically figure out the equivalent nodal loads that go with that temperature field. Likewise with the other forces. Civil engineering codes will often automatically give you pressure equivalent nodal loads on a surface if the pressure is either constant or linear with the dimension. And the reason being there that dams and other bodies exposed to hydrostatic forces often have linearly varying pressures on the face of a surface. Now, it's good that this happens, that the codes have implemented this help for the user, because the older way of doing lumped loads is starting to get tough when we get to the higher order finite elements. It's not much trouble when you have 2 nodes on a side and the redistribution is somewhat along linear ideas. But when you have what are called parabolic elements with 3 nodes on a side, then the shape functions become more exotic, and the actual work equivalent loads sometimes even go in the opposite direction that you might think. So it's not so obvious, and it is therefore good that the codes are doing this for you. I've used the word work equivalent loads now, and some people prefer that term. Pre-strain has become used quite a bit, and primarily because of thermal stress problems, more so than pre-stress. And lastly, it's probably wise modeling practice to put your mid-side nodes literally at the middle point of a side on a finite element. And the reason being that codes in the past have sometimes taken a shortcut and have assumed that that's where the node is, and they don't really do the integration involved, but only have done it in a general sense, perhaps with what amounts to a Simpson's rule, assuming equally spaced nodes, you see. So you would be a little bit more bulletproof if you do literally put mid-side nodes at the mid-side, if you want to avoid that possibility. Now, I don't know of major codes nowadays that have made that assumption. The last element that I know of in one of the major codes was taken out on the order of two or 3 years ago, where that kind of an assumption was made. But nevertheless, I think for the near future it would be wise modeling practice. It is helpful now to apply our new theory to the simplest finite element that one can use, which is the truss element or line element. Here is a two-noded truss, and it has only axial displacements and axial forces. And we'll look at the tension compression characteristics of this body. One of the forms for stiffness that we found involved the shape function. So this is a handy form for us to look at. And then the equivalent nodal loads for this element would involve really only line loads, because lateral loads, there are other moments, and volume loads and other things don't make much sense in this problem. So here's a candidate line load that I'm showing below, and we'll try to find the equivalent nodal loads for that. It's a triangular distribution. But remember that that is a distribution of forces along the axis, and so you have to actually show them in the following form, where they are increasing along the axis like this. And then unfortunately a person has to plot this to be meaningful in a non-physical context like this. So don't be deceived by the direction of the figure below, that those loads are really axial loads. Now, the heart of all of our calculations is based on the shape function approach. So it's indeed, how do you interpolate what goes on in the interior of the element from knowledge of what happens at the nodes. These shape functions that we have dealt with so much now come to our rescue. N1 here is the shape function with a unit value at the first node and 0 at the second. And N2 is the converse, going 0 to 1. We figured these out before, and they're also quite easy to calculate just by the equation of a straight line. So we can explicitly write those out for our problem, showing how each of the nodal displacements affects the internal displacement field in the problem, and giving us this field displacement. Fortunately, this little element is simple, and so the internal workings are all one-dimensional. So for one-dimensional elasticity, it's rather easy to say that the stress is related to the strain through Young's modulus only, and that the strain displacement law is given by this derivative. So previously we had general symbols for these matrix quantities. For instance, the generalized Hooke's law now becomes just Young's modulus, and the strain displacement law becomes just this simple derivative. So we start out by finding the strain matrix B, which was defined to be the strain displacement law times the shape functions. And I've rewritten that here, where the strain displacement law is the derivative. The shape functions we showed in the previous slide are linear functions of x. And when you take the derivative, you get these constants in the strain law. And then you would call this a constant strain element. We'll do the stiffness calculation first. Our stiffness now can be formed from the BGB law, and we can put in those constant strain mappings that we just found. We bring in the Young's modulus for the material law, the generalized Hooke's law. Now, matrix products like this can be done in any order, so we'll multiply out the back two matrices, where the 1 by 1 matrix just becomes a constant multiplying in. Then we have this interesting, very interesting product of matrices. And for some of you, this may be the first time you've seen such a strange situation, because this matrix on the left is one row and, let's see, it's 2 rows and 1 column. It's a 2 by 1. And the one on the right is a 1 by 2. Now, in order to be able to do that multiplication, you have to have conforming matrices, and that means that the terms that are summed over have to have the same number of terms, and that is true. Then you remain with the number of rows from the first matrix and the number of columns from the second in your product form, which we get below here, and so indeed we get a 2 by 2 matrix. So now you are actually expanding the size of your matrices by that multiplication. People who are a little rusty on matrix multiplication should gradually work with this, and you'll become comfortable with it after a while. You can use a summation form also if you feel that you're getting into trouble, and sometimes that's an alternate way to look at it. But in any event, row here times column here will yield this first term, and then likewise row here times column here yields the second term, and so on. And you fill out this integrand. Now, it turns out that the integral of a matrix is the same as the matrix with the integrals taken term by term. That's not obvious, but it shows how placid the integral operator is and the matrix operator, or the matrix notation, because they can be interchanged in that way. And so now you have to integrate these quantities at an element level. That's pretty simple because those are all constant integrands, and they just multiply up, bringing up a length scale when you do the integration. Well, the result of that operation is a matrix that turns out to be the same as the one that we got earlier from equilibrium ideas in our second lecture of this series. Here it is. EA over L is a common term with pluses and minuses, which is more obvious in the second version. And so we have been successful to use an energy method, and when we can compare, we get the same answer as equilibrium. Of course, our real thrust here is that we can use the energy method even when you cannot get the element by equilibrium, but here we're able to compare.